Good evening. I have good news. The College of Arts, Letters, and Sciences is supportive of our seminar series. So that means that food might be coming with it, even if we don't get food and all that stuff, which I'll probably just pay for myself if we need to go down that road.
Oh, that's so nice.
Or we can do a potluck.
Yeah.
Sounds good. So our first one that we have officially scheduled is March 27th. Do you know what else is happening that night? Exam 2. Can you guys, so I know it's not the best night ever to do this, but I do not want to give up the opportunity. This is the woman who studies viruses and how you can use them as delivery vehicles for targeted therapy of ovarian cancer. And she is found an ovarian cancer survivor in the network to come and talk about the patient side of that as well as the basic research side. So they said they could come that day. I didn't want to turn them down. I figured that would be worthwhile. Can you raise your hands if you would come to that 4 o'clock on March 27th, the day of the exam 2? Okay, so we have about 15 hands raised. I am going to be pushing that. Oh, sorry. I will be pushing that out via announcement as well. Can we give it to... we're also looking at getting other people, but that's the first time it's available, so we will have non-people from this class. Invite anyone. Invite your friends. If anyone's interested in medicine or medicinal research or just interested in the ideas that we think about. Danielle?
Is it possible you could talk to another professor?
Okay, I can't hear her, guys. Can you help me out? Sorry, can you say again, Danielle?
Is it possible you could talk to my other professor and give me an excuse for class?
I think that's going to be hard. You can let your professor know this is happening if they want to know anything about it. I'm happy to talk to them, but I'm not going to excuse anyone.
Would you excuse us if there was something during this class?
You're not required to be here. So you can decide to come here. If there's something more important, you do it. All right. Second thing, if you have completed your exam wrapper or want to complete your exam wrapper, please turn that in now. If you don't turn it in now, then it will be counted as late, and you won't be able to get all the credit back. So please turn that in now. Thank you, Logan. Should pile here.
Oh, the other file. Is it this one?
Yeah.
Okay.
So let me ask a question. Mohammed, are you helping us out here? Thank you. You as well, Nabil. We have a ton to do today. So I'm going to ask one really quick question, and I'm going to ask you guys to be really focused and help me move forward. Was this exam wrapper useful?
Yes.
Okay. The final exam is cumulative. One of the main reasons I do the exam wrapper is to have you make sure that you try as hard as you can to master the material at the time, because if it's not a priority right now, you're not going to do it up until the final exam, and then it's going to be so far in the past you're going to forget about it. So I do not plan on doing this for exam 2. It will not happen for exam 3, because exam 3 is the last day of class, so there is no possibility for exam wrapper. So for exam 2, I highly recommend, whether we do an exam wrapper or not, plan on it not happening, take this practice. Look at your exams from this class, from other classes. Think about how you can better learn from the material in the class. Use the assessment as an opportunity to learn. I think it is a very valuable practice. I've heard very few people who have said I did it and it was a waste of my time. It's nice if it's incentivized by points too. All right, so the reason why today's class is going to be a bit intense is, one, because you guys have already been working with some of these concepts before. 2, the semester of Gen Chem 2 has a final exam that is written by the American Chemical Society. That exam has certain topics in it, some that I overemphasize, some that I underemphasize. The topics that I underemphasize are still going to be on the exam, and I will hopefully be able to de-emphasize their impact on your grade. But to make sure that we have as much support as I can give you to prepare you for that exam, I have a lot of things in today's class, but there's some things that I don't have time to dive into. What I've done is I've included some of those on your homework for this weekend. I don't think that I think they are doable in the homework format. It is about what happens if you have a reaction and instead of happens in one step, it happens in 2 steps. How do we know if it happens in 2 steps? That kind of thing. So I highly advise you to start working on that a little earlier than not, and post questions to Blackboard discussions. Look for, it is guided, so it gives you opportunities to learn from that. It drives back to the book. So I think everything's explained in there, but I'm not 100% sure that you'll have everything you need. Use the community. Please don't wait until Sunday night to start if you can help. It's going to be a lot harder to get feedback. Homework is due Sunday night. Post-quiz opens, I think, Saturday morning, closes Monday night. Next week's pre-quizzes are up, and I'll generate the homework soon. That will be due at the end of spring break, I guess. There's no point in having it due at the end of next week. So this kind of gets us into most of Exam 2 territory. There's going to be a little bit on the day before the exam on the 25th of March. All right, so this question hopefully looks somewhat familiar, at least the first half of it. You guys recognize that table? When did we see that table? Talk to your neighbor about when we saw that table, how we might have used this table to determine this information. Make sure you're 100% on how we can get to that part before we start answering the quicker question for today. Okay, we're not clicking in the answer yet. We're good. I want to know how we would get the stuff in the white box on the right from that table. Kayla?
So, you look at the concentration. So for NO, you look at where the O2 is constant, and you compare the change in concentration and the change in the rates, and then you would do the same thing for O2.
Okay, and so we're looking at 3 completely different experiments where we change how much reactant we start with. Where have you guys seen this besides class? You guys did this in lab, right? I hear in some yeses. Okay, if you don't understand that you did this in lab, go back and review your labs. Because that's kind of an important take-home. So if we do the experiment once, we start with these initial concentrations of our 2 reactants. We see, well, how fast is the tangent to the slope, right? The initial rate of the reaction. And then if we change only one of the reactants, right? We change the initial concentration of O2. Does that influence the rate of reaction? Yes or no? Does changing the initial concentration of NO compared to experiment 1, does that change the initial rate of reaction? What can we do with that information? Couldn't hear you?
Oh, you can plug it into the integrated rate law equation for...
Is it the integrated rate law? So if we determine how the rate changes with concentration of NO, and we determine that that's exponential, that's squared, what does that do? What do we do? We determine that what's second order? NO is second order, so we write our differentiated rate law with the concentration of NO squared influences the rate of reaction, right? And then we say that O2, we find that if we change the concentration of O2, the rate change is proportional to that. So that means that O2 is first order. How do we find the rate constant? Angel? So we have the K, but how did we find that? You guys found this. This is a refresher from like a week ago. So we picked one experiment We have a known value for each concentration and the rate of reaction, so we solve for the one unknown. Okay, I just wanted to bring us all back in the same place. So now that we know what the rate constant is, we know what the rate order is for each of our reactants and the overall reaction, go ahead and answer this question. Go ahead and talk to your neighbors. Try to figure out how this information, differentiated rate law, can be used to solve this problem.
So if it's 1 second
Well, yeah, because why would you, so I can because you would take the coefficient of the
Yeah. But since this is already one,
Well, no.
so yeah, you're right.
now we're trying to solve for
It's not what it seems. It's not what it seems. It's all an illusion.
Alright, we have 9 quick responses. Do we have an idea of how to approach this? If you don't have an idea yet of how to approach it, then please raise your hand. There are 6 of us here to help.
I started trying to use the formula, but I realized that that's concentration of
Started out.
So what kind of equation do you need? What variables? Do you have an equation or a set of equations that has time, initial, and final concentration?
Yes, but this is what I did. Exactly, so I don't know.
O2 is third.
No, all two.
That's how I would know.
But I got like the X-ray number. We have to find the case, right? Initially it was that.
Oh, it
What's the
We're doing all these business notes today.
All right, everyone got pretty quiet. So shall we talk through this? Let's go really high level. I don't want to talk numbers right now. I want to talk process. So is someone willing to share what insight they have from reading the question carefully and then thinking about how this pieces together a few different concepts that we've been working on? Go ahead.
Okay, so
Go birthday girl.
we're trying to figure out how much O2, so then once I finally realized that's what was going on, I realized I need to look for a formula that would allow me to see that when considering time. So when looking at O2 in the rate formula, I can see that's first order. So then I could go and look at my formulas, which we do have a first order equation for that. That would use
What do you
time.
mean? For that, meaning it has time and...
It has time and K, and we can go and find concentration of O2 from there.
Okay, if we know the initial, we could find the final. All right, did you guys get that far? So what I'm trying to pull out here is that this equation can be useful if I ask you, if experiment 1 was taken and then we did experiment 4, we changed the initial concentration, what is the rate? Right, we can use this equation for that. But if I ask you what's a concentration at a future time, that equation doesn't help you at all. So if we use the first order kinetic integrated rate law, we know initial concentration. How do we know initial concentration? Experiment 1, right? So initial concentration of NO, initial concentration of O2. Do we expect the number to be bigger or smaller than that in the end?
Smaller.
It's going to have to go down because it's a reactant. So if you get a number that's bigger than that, you know that you might have done your inverse logs improperly or used an improper formula. All right? So if we go through the process then of... I think I have a pencil here somewhere. Maybe not. I didn't take it out yet. So let's write this out then. So we know that it's first order because that was determined for O2. So the equation that we have available to us, natural log of the final concentration, natural log of the initial concentration minus K times T. What is our T in this equation? 37.5 seconds. How do I know I can use seconds in this formula? Units of K are in seconds, so we don't have to convert to a different unit of time. So then we have 37.5. What is our ln of initial concentration? Ln of 0.0100 molar minus We have our K value, 1.0 molar second. And then we can find natural log of the concentration at that time.
But we have to do that.
So mathematically, can someone share with me what the value of the right side of this equation was before we did any inverse logs? Can you say it again? Negative. Does that sound right? Equals ln of, I'm going to do that diagonal. So then how do we find that initial concentration? So E to the negative 42.105 is our initial concentration. What value did you find for that?
I got 5.17, or rather 5.18 times 10 to the negative 19.
That's our final concentration.
Capital N.
It's a concentration. How do we know it's molarity? Units are really important for that. Okay? If I asked you guys to find the half-life, would you be able to find the half-life of this reaction? That reactant. John?
Where did we utilize time in that, though? The seconds, where did we plug that in?
So that was...
You didn't write it.
Oh, I didn't write it out.
It's just times 30.
So seconds is on the top, seconds is on the bottom. Sorry, sloppy not writing all the variables in there. So we filled in this whole equation with the knowns. We solved for the unknown, doing inverse log to do that. So does that seem reasonable? Does that seem like there should be, is it less than 0.0100 molar? So is it a lot less? Is it a little bit less? A lot less. 10 to the negative 19th molar. That's pretty ridiculous. So what does that tell us about the speed of this reaction? 37 seconds and everything's gone. Really, really, really high rate constant. So kind of keep that in mind, that this rate constant is absurdly high. You'll find a lot of other ones when you do calculations. They'll be 10 to the negative 4th, 10 to the negative 8th. Those are more typical rate constants. This is a really fast rate constant. So what I'm trying to show you guys here is how to think about the connectivity between differentiated rate law and integrated rate law. If we find the rate constant in one, we can apply it to the other one, and vice versa. If we find the rate constant through the half-life version of the integrated rate laws, we can use that in any of the other equations as well. So my objectives for you guys today, and by the way, I did take a look here, and people wrote it a number of different ways, but I saw a lot of similar answers. One thing that does concern me is the negative 18th versus 19th. So make really sure that you are comfortable doing natural log and taking the inverse of that, e to the. So we're going to spend most of the rest of the class talking about how temperature and activation energy alter a reaction coordinate diagram. And to do that, we're going to watch a little video here in 1 second. So that all boils down to the Arrhenius equation. So far, we've talked about reactions saying you can use a differentiated or integrated rate law or the half-life equation, which is a version of the integrated rate law when you only talk about a half decrease. We haven't talked about those reactions at different temperatures or with catalysts. So that's what our goal is for today. So we're just talking about that qualitatively. What does that mean big picture? What does it mean calculation-wise? And we're going to be using some experimental data predicting how the rate constant changes with temperature. There's a lot of talk these days about climate change and how we need to do something to get stop using fossil fuels, taking this solid carbon source or liquid carbon source and putting it into the atmosphere and warming our climate, influencing a number of other things across the planet. So hydrogen and hydrogen fuel cells are an option for that. If we just look at that reaction, hydrogen and oxygen gas, you burn those and you form water. This is what's called a reaction coordinate diagram, and this is a little bit of an oversimplified reaction coordinate diagram. By looking at this, we have a reactants on the left, our products on the right. Time is not involved at all, but it's saying that if we have all reactants, start of the reaction, the end of the reaction, if it were like that. What's missing from this graph? And maybe I'll give a hint. If we have hydrogen and oxygen gas combined and running into each other, is it going to go boom? Have you ever seen hydrogen and oxygen in the same place at the same time? Gas, H2 and O2. Here, right? The air has hydrogen gas and it has oxygen gas and it's not blowing up right now. So what's missing from this diagram that would help us realize? So there needs to be some initial input of energy. Something has to be invested before, so a spark, right? And higher concentrations. And there's a few other things. But the biggest thing that's missing from this diagram is that you have to put energy in order to generate these products. So what we're going to be talking about today is what those diagrams look like and how the Arrhenius equation allows us to kind of interpret those diagrams. So let's start with, if I can find the headphone jack. Whoa. Come on, buddy. Why is there no sound?
Turn it up on your pad, maybe?
It has nothing to do with the pad. It has to do with this.
On and off.
Oh, wait.
Easy. If you can't beat the clown, I don't think you again.
All right. So, the reason I show this is because in my mental picture, right, we have mental models of how things work. This is activation energy. Makes total sense, right? We're going to come back to it a few times, but thinking about how much energy does it take to get the molecules, the reactants, up to the peak of that energy. If they don't get to the peak, they're not going into the clown's stomach, right? So let's keep that model in mind. So we have to think about a few things. In order to get to that peak, the molecules have to have enough energy to collide. They have to be moving around. If you take hydrogen and oxygen, you have them in two separate containers, they're obviously not going to react. If you put them in the same container and they're really cold, they're not going to react either because they're not colliding. So they have to run into each other. You have to have some initial amount of energy, right? Enough energy to get up to the top of the clown's tongue. And they have to hit in the right orientation. It has to be the right part of the molecules, which doesn't apply to the tongue at all. But the teeth is the bad part. But yeah, okay. Fair enough. All right, so we're going to talk through this a lot. So let's go ahead and take a look at another reaction coordinate diagram that actually does show all the different components. So which value represents the initial energy of our reactants out of these options here? Couple more seconds. All right. So overwhelmingly, we have D. So on this scale, on this axis right here, 10 is the amount of energy of our reactants. What is the amount of energy of our products then? So 5 is the energy of our reactants. And then I want you thinking about what the difference is of the entire reaction. We'll kind of step through some questions that will lead us there. So the part let me get rid of this, get it over the side. The part that's of a lot of interest to us in this part of the course is thinking about the transition state as well. That the molecules collided, they had enough energy, and they were the right orientation, so they get to a transition state. And then they can proceed to products, but if they don't get there, they can't do that. Looks like our numbers went away. It's interesting. So based on this diagram, which of these three is the most stable? Unstable. Thank you. Partial reading doesn't get you very far.
That's a nice word.
A couple more seconds. All right, so the class responded, a majority of people say that the transition state is the most unstable or the highest energy state. Think about that golf ball going to the top of the clown's tongue versus sitting right in front of Happy Gilmore versus all the way down in the pits of the clown, right? When it's sitting up top there, it's fairly unstable or required energy to get there, and it's the least stable part of the graph. Which is the most stable then? 5-second answer to this one. Nice. It was 15 seconds, but all right, I agree. Products in this diagram are the most stable. Is that always the case? All right. So which of these two arrows represent the total, or sorry, which of the arrows represent the total change in energy from the reactants to the products? A, B, or the combination of the two? I just want you guys dispersed in amongst the group. Okay?
You were just discussing about.
All right, we have a little less consensus on this one. Can I have someone describe their answer to this? We hear from new voices. Josh?
I put B because it starts at a certain point and ends at a certain point. What happens in between is just great, but it starts and ends. So total change would be B.
Great, I love it. And I kind of set us up for that a little bit by saying what is the energy we're starting at, what is the energy we're ending at. The path in between can be multiple different ways. So a lot of the ways people talk about this is if you decide to go from a village on one side of the Ozarks to the other side of the Ozark mountain peak pinnacle, let's say. You go from one side of Pinnacle to the other side of Pinnacle because that's a huge mountain. Right? You can spend as much energy as you want getting from one side to the other. Or you can just walk around the base trail. You decide to go up and down, it's still the same point A and point B, but you did a whole different path to get there, and that's fine, like Josh said. But it means that the two starting and ending point are not going to change where they are relative to each other. So I absolutely agree with the majority of the class that B represents the total change in energy from reactants to products. So then, I can't remember if I asked this or not, what is the arrow A represent? All right, so that was what was missing from that first graph. And that activation energy can be influenced in a few different ways. What is the most common way we change the activation energy? Catalysts. All right. I believe we have one more question that relates to this. Is this an endothermic or an exothermic reaction? Go ahead and click in your response. All right, go check with someone else. You guys are not in agreement. Refresh. I feel like we got a lot of positive energy in this class tonight. It's awesome. All right, we ended up coming nearly to a consensus on this. About a 90% consensus. So this is the definition of an exothermic, that it starts at a certain energy, the products are more stable. So what happens to the energy change that happened? It's released, it's free, go away, right? So exo means to the outside. This is an exothermic reaction. Do endothermic reactions exist? What would the diagram look like for those? Flip, okay? And one of the things we're going to talk about today is that this exact reaction, whatever this reaction is, can occur in reverse. So next week we start talking about equilibrium. In the lab this week you've been already beginning talking about equilibrium. Most reactions are reversible. And so if this reaction was reversed, and we had all products to start with, this diagram would be exactly what you described. It would be an endothermic reaction. It would be flipped entirely to the other side. Would that change anything about this graph? Would delta E, the total change in energy from reactants to products, be any different? Great, the sign would change. It would need an input of energy overall, an endothermic reaction. Would anything else change? Would the activation energy change? Talk to your neighbor. Try to decide whether the activation energy of the reverse reaction is the same as the forward reaction.
We got a bigger hill to climb.
Okay, I'd like to hear from someone new. Describe whether they think the activation energy of the reverse reaction would be the same or different, and why. New voice. You've already shared today. I'm going to try to give lots of voices a chance. Colin?
I said it would be different because if we flip them, that dotted line that goes from where the beginning energy is now lower. So I guess to get to that top of the transition state, you need more energy.
So if we're thinking about our reactants being over here, they would need this much energy to get to that point of the intermediate. If they were down here instead, they had a much higher hill to climb. So the activation energy of the reverse reaction is this. So rev, you'll see a lot of times for a reverse reaction. So overall, the plot will be very similar. It'll be inverted, but that changes a couple features about it, the sign of delta E and the activation energy. All right, we've already answered that. Let's see where you guys stand with this question. How about we change the temperature? What happens to that activation energy? Go ahead and talk to your neighbor and click in your response. We are not so sure about this answer. Should I show the results?
Yes.
Almost a 1 to 2 to 1. All right, so we're going to come back to that. So let's think about what it takes for a chemical reaction to occur. I promise we'll come back to that. But I want you thinking about building a mental model, and I'm going to help you build a mental model that aligns with what we find in nature. So let's say that we have a chemical reaction. We have a reaction between Cl2 and NO. In order for these to react, we're going to have one of those chlorines transferred to the nitrogen. What has to happen for this reaction to occur? Okay, so a little bit down the road, we have to have a bond breaking. What has to happen before we get to a bond breaking?
The collision.
They have to touch each other, right? They're not just going to like, hey, I'll toss you a chlorine atom. Right? So there has to be a physical collision, which is why solutions are so important. If we have solutions, those molecules are moving freely, and there's a higher chance they'll run into each other. If we have solids, then you can kind of like crush them together. A lot of times you do mortar and pestle. If you're an organic chemist and you're trying to make a reaction go, you can actually grind them together. But just throwing solids together usually doesn't do too much of a reaction. Okay, so they have to hit each other. What else has to happen? What do you mean proper orientation?
That's just what you said earlier.
That's a good listener. What does that mean? Where is that chlorine going to transfer from and to? So it's transferring from one of the chlorine bonds to the nitrogen. So what happens if the oxygen hits the Cl2?
Nothing.
Nothing. So that's the right orientation. That's what that means. Is the nitrogen has to be the part that collides. Okay? And then not only do they have to collide, but I heard some people say it has to have enough energy or speed, right? So we're going to start down here at a lower, more stable set of reactants. As those combine or collide with each other, we're going to assume that they had enough energy and they're colliding with the right orientation. If this NO was turned around the other way, they would bounce off each other and we wouldn't have that reaction. We might have another reaction if there's multiple pathways possible. All right, so then our first question here is at this transition state where we're at the least stable, what outcome is likely from here? Go ahead and click in your response. They have hit each other. We're at the transition state. We have that ball on top of the clown's tongue. All right, convince someone else of your logic because you guys are split 50-50 right now.
Oh, because of I did this with chemistry and I
It depends on the reaction. Yeah. There's a huge amount of difference between different reactions. All right, you guys came to a good conclusion?
Nope. Big argument.
So let's take a look. Let's see what happens.
Nothing. Wow.
An option, right? You're at the least stable point. You have bonds in transition, partial bonds formed, partial bonds breaking. You could also go from the transition state to products. Okay? At that transition state, there's a lot of factors that come into play, and the reaction at that point can go either way. The higher the activation energy is, the more that reaction is said to be kinetically favored. So that has to do with the collision and orientation and how much energy it takes to get to that certain point. There's also thermodynamic control, which is about the relative height of the start and the end. So I think your homework has a little bit on that, and I'm happy to let you guys explore that more there. All right. We talked about that earlier. When you increase the temperature, what happens to reaction speed usually? And then think about what that means for this graph. Closing out. Am I asking too easy questions today? Is that why we have almost complete consensus? Alright, so as we speed up a reaction, we know that the reaction speeds up. It gets to the most stable point more quickly. Whether that's all products or all reactants, it doesn't. We're not saying that. Right, we could be talking about this reaction. If we heat it up, we're going to have a distribution of reactants and products. In equilibrium, we'll talk about where that distribution lies. And it relates to the rate of the forward reaction and the rate of the reverse reaction, which is what our supplemental instruction this week is. So just in case you do not come to supplemental instruction this week, I think I said it in the announcement yesterday, we will do Chem Activity 37 that I handed out like a week and a half ago, stapled to 36. Remember, we have to pull those apart. And we're not going to do Model 1 in workshop. Still useful, but we only have limited time in supplemental instruction workshop. So we're doing Model 2 of Activity 37, and then we're doing Activity 38 that I handed out tonight. So please make sure that you bring those with you. 37 Model 2 and 38. All right, so if we think about why the reaction speeds up. Logan?
So I said it would speed up because the energy, so one that we talked about earlier, that the activation energy will be less. So I guess you could say that it'll happen more frequently. And they'll be moving faster, so there'll be more collisions for a higher possibility of them making the reaction.
Okay, so by having them move faster, there's a higher rate of collision. Fantastic. And if there's a higher rate, there's a higher propensity for them being in the right orientation and having the right amount of energy when they collide. Does that mean that the activation energy is going to get less? This graph will not change. If we change temperature, the only thing that will change is what fraction of the molecules down here have the energy and frequency of collision to get to that transition state. So, do you guys feel comfortable with this now? Then you have a question you want to ask the whole class, or? Okay. I'll come around in 1 second. I think this is. All right, closing out.
I wasn't asking a question, I was saying B and sign, sorry.
So my wife calls me.
Just B, like Vincent, or?
Like the letter B. Okay. I think we have pretty much everyone on the same page here. we want to be thinking about what changes and what does not about this graph. Bree?
I'm just trying to use what the H stands for on your action.
Good question. So in my class during first semester, I spent a little bit of time talking about this. Total change in energy of a reaction is usually what we talk about, but that's both how much work is done and what the change in heat is, or enthalpy, H. And so as chemists, we like to ignore work and just look at the change in heat because it's easier to measure. So a lot of times enthalpy, H, will be interchangeably used for energy because chemists are lazy. Or we're really smart and we get rid of the work as a function and we focus on the heat transfer. All right, we've already talked about that. Correct? So we talked about the activation energy for the forward versus the reverse reaction. And in this diagram, it kind of exaggerates that. It shows exactly what that change in energy is. That if you run the reaction going forward, we have a lot of energy to input. If we ran the reaction starting from products and tried to generate some reactants or started all here, then we'd have a much lower activation energy to get over in order for that reaction to proceed. So do you think that this reaction is going to form products, and when we're done, we're going to have 0 reactants in all products? I think there's going to be a mixture. What do you think there's going to be more of in your mixture, reactants or products? Based on just looking at this diagram, talk about thermodynamic control, we're going to have more reactants than products. Do we need to do this question? All right, go ahead. Question 10? We talked about activation energy. We haven't talked about this specific point yet. Couple more seconds. Can I hear from Jason, Matthew, Kayla's group?
You did not agree.
We all
Great.
have different answers.
So, can you share one that you discussed?
I said it doesn't change. The activation energy will change with increased temperature, but not the whatever that is.
Do you guys agree with that? So is the activation energy going to change with an increase in temperature? Sorry, buddy. Okay, so activation energy stays the same. So what does change with an increase in temperature? Jonathan, I heard you guys discussing over here. Lindsay, or why does the rate of the reaction change when you increase the temperature? What about
The orientation, kind of like what we're there's more collisions, there's more kinetic energy in the system.
So you have more collisions happening, you have them with a higher pace, you have more of them, more collisions that happen with the right orientation. So you still have the same barrier in place, you still have the same stability of your reactants and products. The only thing that changes is how many of your molecules are able to go through that reaction. So the two things that don't change with temperature are activation energy and
The total energy change.
delta E for the reaction. Do not change when we change temperature. All right, so let's look at what that means for calculations. So that was answer A, correct?
I call that being right.
let's do a diagram. We love diagrams, right? All right, let's do a 15-second question on this one.
15.
All right, 15 seconds. All right, I'm trying to get you guys through as much as we can today, and I'm trying to do it with giving you time, so help me out here. All right, all molecules do not move at the same speed. We have a distribution of molecules, and on the next question, you're going to draw it. What does that distribution of molecular speed look like at a particular temperature? Okay? So think about what we did before with speed of molecules. What was that related to? Remember on the exam, you guys did the exam wrapper, I had you draw a diagram almost exactly like this. So we were talking about vaporization, how many of the molecules in a liquid are moving fast enough to overcome the molecular forces and become a gas. So think about it, if we're just looking at a body of gas molecules, are there any standing still at any point in time? Are there any at a higher speed? What does that distribution look like? Go ahead and take 30 seconds. Draw in pencil what your distribution of molecular speeds would look like for a particular temperature. Anyone like to draw?
Me? No, I'm good.
Anyone want to draw it?
I'm good.
I'll draw the wrong thing, but I'll draw it.
Here, you can just use mine as a template. I don't know.
And it's gonna go something like that.
Oh.
And
Oh.
I did not mean to do that. Where's the eraser? Thank you.
No, it's fine, bro. You're good.
Yes,
Like that.
All right, so Anthony, tell us about what you drew.
I drew a purple line on a graph that's the comparison of percent of molecules versus molecular energy.
Okay, so why did you decide to draw the way you did?
Well, there's going to be, it's obviously going to be a distribution of which are going at a different speed, but I thought perhaps there could be a very, very minute few that aren't moving, even though they're a gas, and then there's going to be more that are going to be moving at a higher speed because they are a gas, rather than if they were in a liquid state.
Yeah, so they're probably not going to be standing still for very long, but if you took a snapshot and measured speed, or did really quick images one right after the other, there's some that are not going to move very far in that amount of time. So I agree that at any point in time that some look like they're standing still, it's not going to be for very long, or else it would be a liquid, right? But then as you look at higher speeds, you're going to have a lot of molecules that are moving pretty quickly because it's a gas and they're pretty far apart, so they're moving around. And then you have some that are tailing off at a higher speed. So then, what does this mean as far as if these are molecules that are going to participate in a reaction? What would we draw a vertical line representing? So if I draw a vertical line, let's say there. What does that vertical line represent from our discussions that we've been having so far? Narina? You following the conversation about what that vertical line would mean, or any ideas? Yeah.
Yes.
So what do you think that vertical line represents? If that's all the molecular speeds, and we put a vertical line somewhere over there, what does that represent?
The activation.
Why?
Because according to our test the last lecture, that is after the molecules pass that point. Okay, I can't stand now.
Someone want to help out?
So energy needed to overcome the intermolecular forces to go through a phase change.
True. On our other graph, that was absolutely right. And that was the distribution of speeds in a liquid, and that was talking about how much speed is needed to overcome the intermolecular forces, and they have to be at the surface, remember? It wasn't just if they're in the middle of the liquid and they're going really fast, they're not just going to automatically become a gas. In this graph, it's a bit different, though. So we're talking about molecules moving around and their propensity to react. So if we're calling that line activation energy, what does it mean about to the left and to the right? Logan?
It goes back to saying, like we said earlier, if you were to heat up a solution, that more collisions, and there would be like increase the propensity of them being in the right place and having the right amount of energy. So that would be like where it would need to be, and it's a small percentage, so that would make sense logically. That like not all of them are gonna have the exact right angle, and not all of them are gonna react the same.
So I'm going to come back to that last point in a second because I love where you're going with this. So if we talk about molecules, they're bumping into each other, but they're going super slow, they're not very likely to react, right? Even if they have the right orientation. If they're going above a certain molecular speed or have a certain amount of energy, right, we can kind of equate kinetic energy with molecular speed or molecular energy. They have to have at least this much energy when they collide to start breaking one set of bonds and forming a new set. But what if they have that energy or that speed and they don't collide with something? Then there's not going to be a reaction, right? So we need to think about that's enough energy that if they do collide and they have the right orientation, that they can go through that reaction, or they might come back after. So what would be different about this graph if we, or how might we get more molecules, using your terminology, how do we get more molecules to overcome the activation energy in this graph? Josh, wait, do you want to draw it? No. Yes? All right, draw what we would need to do.
So if it's increased temperature, the graph wouldn't change. Well, we shouldn't expect it to, but it would require the line should shift. You don't like that? If the energy is higher.
All right, so pause. Pause. That was one option. All right, and then I heard Angel. Angel going, So, Angel, what would you say?
To Logan next. We are allowed to have different opinions.
This is right.
It's like we're the only adults here that are allowed to have different opinions. Oh, that's good. Okay, way to go.
So, Angel, as I'm walking back up front, can you explain what you drew and why?
You said that temperature does not affect activation energy.
Boom! Okay, so what did you do instead? What happens when we...
But more of them can reach that, can push past that activation energy point and get into the...
So if we could shift that graph to the right, because activation energy is not changing what we're doing. We shift that graph to the right, now our proportion of molecules that have enough energy in the right collision, right, with the right orientation, to overcome that activation energy increases. What would you do to shift the purple graph to the red dotted graph? Warm it up. So, Bree, to your point, it does have a lot of similarities to what we talked about with vapor pressure and how much energy is needed to overcome the intermolecular forces, right? Same principles apply, but here it's about colliding. So, Humphrey, go ahead, and then I'll ask one question, follow up on Josh's. So the distribution of speeds can be very similar, but this one is talking about, I think we were talking about in gas molecules. I don't know if I talked about gas specifically. So the idea is that if you have a whole bunch of molecules moving around, if they collide with each other, you have all the molecules at different speeds. So this might be one molecule and the other one would have to be moving around at the same speed, and their collision is what's going to be really important. So similar principle about distribution of speeds, but now instead of overcoming attraction from another, it's about when they collide into something, what happens.
So the graphs look the same.
They have very, very, very similar properties. I'll show you an image from the book here in 1 second. So going off of Josh's point, yes, what he showed could be a way to increase the number of molecules that can go through this reaction. How would we get Josh's shift in the green line to happen? Lynn? Okay. If we add a catalyst, catalysts decrease the activation energy. They give a different pathway to get from point A to point B. They make it easier, lower energy. So instead of going up and over Pinnacle Mountain, we can go to a side point because everything else is blocked off, right? We can go to a little bit easier of a way. It gives us alternative pathways to get from reactants to products. So the one thing I'm going to give you a hard time about, Josh, is you said the temperature will move the activation energy. That's where we're going to harp on.
I was questioning. I was like,
Okay? So both of those approaches are completely legit. You either heat up the sample, and hence more molecules have the speed to collide with each other to go over the activation energy. The other one is you add a catalyst, and with the purple line still, you now have a larger proportion of the molecules that can overcome the new activation energy.
So if we did what Jeff did on the test, would you grade it correct?
If I just said, how do you get more molecules to go through this reaction? And you said I add a catalyst to decrease the activation energy, correct. If we warm up the sample to have more go over the same exact activation energy, correct. If you say we increase temperature to lower the activation energy, incorrect. Hannah?
So what happens to molecules after they pass activation energy? You did say if they collide and like if they hit certain points, but what exactly happens after they hit certain points?
They form products, or they go back and form reactants, one or the other. It gives them the opportunity to be at the transition state that allows them to then distribute amongst the two options. Echo?
So those are not necessarily like the molecules that are vaporized, it's like just the molecules that have the potential to do other things.
To do a chemical reaction, right? So the big difference with the graph that you had on your exam, which was about going from liquid to gas, the same principle applies in that you need to have a certain speed in order for something to happen. There it was to get pulled away from another molecule. Here it has to collide with something. If it doesn't have that speed to collide, it's not going to be able to go through the reaction.
So it's like the percentage of like molecules that could potentially react.
And as you warm up the sample, you have a larger proportion of molecules that are going that speed or higher. David?
Doesn't the height or the percent of molecules go down as you shift to the right?
Yeah, so a slight modification. Angel was drawing freehand, so I would modify this to have the peak a little bit lower, but the shift in peak to the right was really important, and showing that the tail out to the right is there.
Why would you have it a little lower?
So the area under the curve represents the total number of molecules. When you warm it up, you don't have more molecules. You just have them, on average, moving faster. So that means that if the area under the curve is the number of molecules, and you have more out here, it means you have to have less over here. So you have less at the peak. So it'll just be a little bit shallower of a peak. All right. We are running kind of low on time. Can you answer this question now? As the temperature reaction goes up, the overall fraction of particles with enough energy to overcome activation energy. It's true, that's why I'm saying it out loud. Not a clicker. I was trying to do this quickly because we got a lot to do and we still only have 7 minutes left. All right, we're going to increase the number. So this is the diagram you see in your book. And once again, just like when we talked about vapor pressure, I think that diagram with that explanation is super confusing. And so I wanted to show this, but have us work up to it as well. To show lower temperature, higher temperature, distribution of molecules. They do theirs without as much of a tail on the left side as we did. I don't really know, depends on what medium we're in, a lot of different things. The big point for me is that this peak should move a little bit to the right of the warmer sample. You have a larger number of molecules out to the right, and then you have your activation energy change if you have a catalyst. That's all summarized in this figure. So we did that bit by bit. All right, and this is what it looked like when we were talking about vapor pressure. The graphs look very similar. There is a simulation that if you're still not kind of seeing how temperature and activation energy fit in, I would really advise that you guys go and download as JavaScript, so you have to enable JavaScript. But it's linked on the slide, so if you download them after class, you can then download that simulation. Okay, so we've talked a lot about qualitative, like big picture, what happens. But how do we actually get into quantitative descriptions of how fast a reaction occurs with changes in activation energy? Have you guys been playing with this equation in your pre-class quiz? So if we look at our Differentiated rate law, there's nowhere that activation energy exists here, except it's hidden within that. If we look at our integrated rate laws, there's still no activation energy. So the Arrhenius equation is where that plays a role. The rate constant is a constant if you don't change the temperature. As soon as you change the temperature, rate constant is no longer constant. There is actually only one factor that is constant for a reaction, regardless of temperature, activation energy, or any concentration. That is, so gas constant is part of the equation, but this frequency factor. This A is the biggest that your rate constant can ever possibly be for a reaction. If you do a different reaction, your A is going to be different. So if we're talking about the reaction between NO and Cl2, it has an A value. If you change the temperature, A doesn't change. But temperature is in here. Activation energy is in here. And our rate constant changes proportional to the exponential relationship with those variables. So what would give us the highest rate constant that gives us the highest reaction rate? What would we want to do to a reaction to make it go as fast as humanly possible? Love?
Increase temperature and add a catalyst.
Great, so we just talked about the hotter they are, usually the faster reactions go. Okay, there's a certain point at which that no longer becomes true and molecules fall apart. And we'd want a catalyst that would lower the activation energy, lower the bump between them, right? So what would this exponent be if we had a very, 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 very small activation energy, gas constant, and a very, 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 very large temperature? So what does that exponent get close to? Small number on top, really big number on bottom. It's close to 0, right? What's e to the 0? 1. This is the biggest our rate constant can ever be. Because that, in the optimum conditions, is multiplied by 1 to give us our rate constant. You guys see that? So that means that if we, instead of having optimum conditions, we have less than optimum conditions. Let's say that our activation energy is pretty big. We have a pretty low temperature. That means we're going to do e to the negative big number. What does that mean? What does any number to the negative exponent mean? Let's say, what is 5 to the negative 15th? What does that mean?
Really small.
What's another way to rewrite that? 1 over 5 to the 15th. That's a small number, right? We're making a really big denominator by having a big negative exponent. That's true here as well. So, the lower the activation energy, the higher the activation energy becomes, the bigger the negative exponent. The lower the temperature, the smaller the denominator, the bigger the negative exponent. So that's the logic of how these things fit together. If you guys have not taken a turn of going and kind of digging into logarithms, I will tell you that there's one place that's probably the best one-stop shop for learning how to manipulate logarithms. That was pointed out by Janesh. I don't know where Janesh went to. There he is. And it's actually one of our colleagues' pieces of work. It is the LibreText that is linked under our resources. If you go in additional resources on the left side of our Blackboard page, there's a link to Dr. Belford's LibreText for Gen Chem 2. Chapter 14, he has a chapter 14.0 where he has 2 videos on how to manipulate logs in chemistry and how to utilize them and what they mean. That is some of the best 10 minutes you can spend learning about logs. So I have decided that it would be most beneficial to you all for the rest of the semester if we had a quiz on logarithms, an in-class quiz. Because honestly, are you guys going to go out and learn about logs if I don't quiz you on it? Well, if you did already, then you're great. So I am going to, next week, either Monday or Wednesday, it'll probably be Wednesday, I will figure out a way to give you guys a very quick quiz on how to manipulate logarithms based on those 2 videos. So make sure you watch those 2 videos. All right. Have a good night, guys. I will see you guys on Monday. There are a little bit of mathematical ways you can use these equations. And they relate to this equation.